the one that you are going to study this weekend like crazy. If you take this material and you deform it up to here, the second time it's going to be deformed to what stress level? To this stress level. And then let's say we continue here and we unload. If we load it up again, what stress level is it going to reach? Here, like this. You see? This material yielded here, the one that was deformed first time. You see this? Then we plastically deform it, so we go to this point. Then we unload. Then we'll load again. You see, it all automatically deforms at this strength. Then we unload, and we bring it up to here. Then we unload, and we can just follow this strength hardening exponent and make the material harder. Like the body of your car, the hood, the doors, the whole body is made by cold working. And some of you, or most of you, are going to be taking manufacturing processes where you're going to, discuss all of this in much more detail. There are forming operations, by plastic deformation. There's casting and there's miscellaneous. So what kind? Forging, drawing. My major as an undergrad was metals plastic deformation technology. Forging, stamping, drawing, extrusion, all of that. If you look around, you're going to see that all of the metals you see have been put into shape, made into shape by some sort of plastic deformation. Forging. You have a die, and the die have a specific geometry. You take a blank, you heat it up, and then you go boom, and you form your part. It's kind of like, if you played with Play-Doh or Silly Putty when you were little, what do you do with Silly Putty before you start making anything out of it? You deform it in your hands to warm it up, and then it becomes easier, right? So the same thing for the metals. The pressures are so high that basically you can deform metal like you would do Silly Putty with your hands. Drawing, that's how wires are made. There's a die, and then you take a wire and you draw the wire through the die like this. And by doing that, you are reducing the cross-sectional area of the wire. For this process to work, the wire has to be strong enough for you to be able to pull on it. So you design the process so that you can do it. And you can make the wire very long and you reduce the diameter. Rolling is another process. You take a sheet of metal and you have two rollers and you reduce the area like this. Another example is extrusion. It's opposite of drawing. So instead of pulling on that wire, you're pushing the material, a billet, it's called, with a ram through the die. These are examples of metal forming, metals plastic deformation. And you can imagine, some very violent processes are happening, and we are reducing the grain size and forming what's called deformation texture, which I showed you the figures. The grains get elongated along the rolling direction or along the extrusion direction or drawing direction. Any questions about metal forming by plastic deformation? Casting. Casting is basically you take some sort of a form and you melt the metal and you pour this metal into the cast. It's very common and it's relatively inexpensive. You can form very elaborate shapes, but the problem is that the grains are very big and there are a lot of defects. But if you don't care, that's okay. Sand casting. Like engine blocks are made this way. Sand is a very cheap and abundant material to make a mold. And how hot is the metal when you pour it? Well, it depends on the metal, right? But you're above melting temperature, so it's liquid. And you need the material of the form to withstand this kind of temperature. What's that material? It's sand, SiO2. And I will show you a couple of papers I have on it's called spent mold, where the part is actually made from styrofoam. And you can take this styrofoam and put it in the sand with some sort of a binder so that the sand gives you the mold like this. And then when you pour the metal in, the styrofoam gets burned out and you can make a part. Investment casting. You can use wax for something that's low volume and complex shape, like you can make jewelry this way, or sometimes even turbine blades. In the first stage, we take a mold by pouring a plaster or Paris around the wax pattern, and then we let this plaster to harden. And during the second step, we melt this wax, so the wax gives you a cavity of your required geometry. And then the metal is poured in. Die casting is used for high volume production and it's reusable. So you have something like this, but it's used for alloys that are made from low melting temperature alloys because it's made the form is made out of metal. There's continuous casting for like rectangular shapes or cylinders or slabs, and you keep pouring this out and it solidifies and comes out. Here's another example. Here's an example where you would use the foam and then you don't need to get rid of that thing, and the foam gets burned out. And this was dealing with the simulation of the process, how it gets filled with the molten metal. And here's an example of the final shape. You can see it's quite elaborate. You see? Irons that we talked about recently are also made by casting. This is another advanced process that combines casting and rolling. Miscellaneous techniques. Powder metallurgy is very big. So we take powder and compact it and apply high pressure and high temperature for sintering, where these particles make the contact and eventually they form one. The problem with powder metallurgy is stop powder from forming conglomerates. Give me an example where you can have conglomerates in something that's, what's the term? Like sand that can, I forgot the word. Like flour or sugar or salt. It's very humid in Florida. How many of you experience the salt forming clusters? You know what I'm talking about? When you're in Florida, get your salt into a grinder. So you just take the salt and you grind it on demand. That's the best way. All right, guys. Good luck on the exam. Come to the help session tomorrow.